Welcome to Pomodoro Joe for Sunday, September 3rd, 2023. Today we're doing LeetCode problem 62, unique paths. This is a medium problem. There is a robot on an m by n grid. The robot is initially located in the top left corner, right here, i.e. grid at 0, 0. And the robot tries to move to the bottom right corner, i.e. grid m-1, n-1. The robot can only move either down or right at any point in time. Given the two integers m and n, return the number of possible unique paths the robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equal to 2 times 10 to the 9th. Okay, so this is a really good problem, especially if you're new to grid traversals. This is a great problem for grid traversals, for an introduction to grid traversals. So you start up here at 0, 0, and you're trying to get down here at m-1, n-1. Now this robot can only move to the right or down. So you can move all the way right and then go down, or you can move almost all the way right and then go down and then move right again, or you can move right once and down and over. Okay, there are lots of different paths. So one approach is to sort of work backwards. Now we're trying to find the number of paths to reach this final square here. Now, the number of paths to reach this final square is the same as the number of paths to reach this square up here, plus the number of paths to reach the square over here, because we can only reach this final square by moving from this top square down or from this left square right. So if we know how many paths there are to reach this top square, the square just above our final square, we know we can just take one more step down to reach our final square. So the number of paths to reach here plus the number of paths to reach here will be the number of paths to reach our final square. So the number of paths to reach here, we just move down. The number of paths to reach here, we can just move to the right. So we add those two together and we get the number of paths to our final square. All right, so let's put 25 minutes on the Pomodoro timer and we will get started. So there are a couple different ways to approach this. I'm going to start with the simple way first, and then we'll try to refine. So the simple way is to actually just build out our entire grid here. So we'll build out our entire grid, we'll fill it in with zeros, then we'll put our robot down at the very start at 0, 0. There'll be one path to 0, 0. Then we'll just go through every single square to try to find how many unique paths there are to get to that square until we finally get to the last square. Okay. So here's our grid. Our grid will have a row of zeros, and we can do multiplied by n. So this will basically give us a list that's n elements long and it's filled with zeros. And now we want to have m of these lists stacked on top of each other. So we'll say for blank in range m. So this is just a way to build up our grid. So to show that this works, let's just go through and print all the rows. For row and grid, we'll print our row. All right, so this should show our grid. Let's take a look. Now this won't pass our test, but it should show our grid. Cool, so we've got our grid here. It's got a bunch of zeros in it. All right, let's go back. So now that we have our grid, we also know our robot starts at 0, 0. So we can set 0, 0 equal to 1. There's one way for the robot to get to that point. It starts there. So grid at 0, 0 is equal to 1. Now we have to go through every square in our grid, from top to bottom, left to right, until we get to our final square. So for, I'll call it x in range. Now, n is our x value. So I think this is a good point to take a second to talk about our grid coordinates. So our grid will be an m by n grid. Now this is our columns. So our left to right, those are the number of columns we have. So in that case, that is our n value. And top to bottom, that's the number of rows that we have. So that is our m value. So the start up here, this is 0, 0, and our coordinate, our x value, gets greater as we move to the right, and our y value gets greater as we move from top to bottom. So this is a little bit reversed from your general Cartesian coordinates that you might use for graphing in math class, but you'll get used to it. All right, so 0, 0 is in the top left, and we get greater in our x as we go right and greater in our y as we go down. So for every x coordinate in our range n, and then for every y coordinate in range m. Now this is another thing I should talk about. Our rows will come first and our columns will come second in our coordinates here when we're indexing into our grid. So we'll have a y first and then our x. So our grid at y, x, that's just going to be equal to the sum of the unique paths to the cell above us plus the unique paths to the cell to our left. So the grid at this cell will be the sum of the grid's unique paths to the cell just above this cell and the unique paths to the cell just to the left of this cell. So that is going to be y minus 1 and x minus 1. Now let's break this up here. We'll have up, and that's going to be the grid at, let's see, this is going to be y minus 1 and x, but only if our y is greater than 0. Now, if our y is less than or equal to 0, well then we can't have a cell above it. So we do have to have a little bit of an extra protection here. That's if y is greater than 0. Else, well then what's our value? If y isn't, well then else it's going to be 0. There's no cell above us. And then left, well that's going to be grid at y, this y, but it's going to be at x minus 1. But again, we need to have some protection, but that's only if our x is greater than 0. Otherwise, there is no cell to our left, so it'll be 0. So the grid at this point will just be our up plus our left. All right, so now we're going through every cell in our grid. We're going to be adding up all the unique paths coming from either the top cell or the left cell. And at the end, we'll just return our grid at our final cell. Now, this will be m minus 1 and n minus 1. All right, so this should do it. We go through, we initialize our grid. It's going to be m by n grid. We'll fill it with zeros to start, but then we'll update the very first cell, or start cell, with a 1. That's where the robot starts. Then we'll just go through every cell from left to right, top to bottom. We'll check to see the cell above our current cell and to the left of our current cell. Make sure that we're still within our bounds. If we are, then we can sum those two unique paths together to assign that to this cell. At the end, we just return the value that we're storing in our final cell. All right, so there's one more thing that we need to do here. So if we just use this as it is, our grid at 0, 0 will be overridden by zeros. So we actually need to have some special case here. So if x is equal to 0 and y is equal to 0, then we don't want to update this, so we'll just continue. All right, let's give this a shot. Cool, and it works. So let's see if we can pass all the tests. And we pass. And we do okay. No, we don't. We do terribly. We only beat 36% for runtime and 47% for memory. So this is not the best way to do this. So let's jump back here. Now one thing, we are basically initializing an entire grid, going through the entire grid, only to end up with these last 3 cells that we care about. The one above, the one to the left, and the final cell. So what if we didn't do it this way? What if we just kept track of one row at a time? So if we just kept track of our first row, filled this all in, then we move down to the second row, fill that all in, then we move down to the third row, fill that all in. This will save us a ton of processing. Now one thing to note, because we have this first row, there's only one way to get to each one of these cells. There's no cell above. That means this whole first row will be 1s. There's only one way to get to this one, only one way to get to this cell, this cell, this cell, this cell, this cell. So we could just fill this with 1s. Same thing with our columns. There's only one way to get to this very first column. That's by going straight down. All right, so let's do this another way. Let's just keep track of one row at a time. We only need to keep track of this one row, the row that's above, and then we'll calculate our current row. Then we'll swap out our current row for the row that's above. So this becomes the row that's above, and we'll calculate the next row. We can keep doing that until we get down to the very last row, and then we can calculate just the last cell in that row. So let's change some of this. Let's just have a row. So we'll just have a row. Now the very first row starts as 1s, because there's only one way to get to every single one of these cells. So that's 1 times n. All right, and now we need to do something very similar to what we had before. So for every y in range m, so this is for every row. Let's see, we already have the first row, so you can go from 1 to m. That's because we've already filled in this first row with 1s. Next, in here, we'll say for every x in range, and again, we can say 1 to n because we already know the first column will always be a 1. So now in this loop, we're calculating the values for our next row. So our next row, well, we don't really have this yet, but our next row at this cell, or at this column, well, that's going to be equal to, well, this next row, the cell to its left, that's x minus 1, plus the row that's above it, so above row, I'll call it this up row, at this same x coordinate, the same column. All right, now we don't have a next row here, so let's create our next row. So our next row, we're going to fill this with zeros. It's going to start out as 0 times n. All right, so we're going to fill in, we'll have a blank row. That's our next row. And then we do need to start this next row. The next row's column at 0 is equal to 1. So every row starts with column 0 filled with 1. Now this up row is basically just this row that we created here, so I'll just rename this just row. All right. Now that we've gone through all of that, we need to swap out our rows. So the row that is above us, well, that's this next row. So essentially we're going through filling in this next row by using the row that's above. So this current row then becomes the row that's above. So maybe I'll rename some of these so it's easier to follow. So I'll call this row above. Okay, and I'll call this the current row. This makes it easier then, right? So we're calculating our current row. Our current row at this x will be our current row at x minus 1, so we're just looking immediately to our left. And it will add the row above at this x. All right, now our row above becomes our current row. So now we're moving on to the next row, which becomes our current row, and the row above has to take on the values of this current row. All right, and finally we can just return our current row at the last value. So that's going to be at -1. All right. So this one's a little bit trickier to comprehend. The first way we did this, we just went through the entire matrix. We built up our template, we filled it in as we went, and we found the final value at the finish cell. Now this one's a little bit different where we're going to keep track of just one row at a time, figure out that row, then look at the row below it, fill that one out. Keep moving down until we get to the last row. All right, let's run this, see how we do. And we pass. And this works. Let's see if we can pass all the tests. Oh, our current row is only declared inside here. So this will actually, since we're assigning it to our row above, we can actually just return our row above at the last cell. All right, and we pass, and we don't do very well. We only beat 42% for runtime and 47% for memory, so that is not a great solution. That's interesting. I thought this would be much better. Let's try changing some of these names. Let's just call this row. We'll call this next row. Now you notice we're not actually using this y anywhere, so we can actually just rename this underscore. All right, and then this should be fine. Just call it row. Oh wow, that's significantly better. Just by changing the names and a little bit of the formatting, we went from a 42% for runtime to a 92% for runtime. That's a huge win. I'm really surprised by that. All right, I am running out of time and this is kind of a mess, but it's a great problem. I really encourage you to try this one out. Do this one on your own. Again, this is LeetCode problem 62, unique paths. Great problem for an introduction to grid traversal. Okay, well that is it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.